Let's talk about angle bisectors. So I have an angle already drawn for you. This would be angle ABC here in black. Okay, so if I want to draw an angle bisector, that's basically just a ray that divides that angle into two congruent angle measurements. Okay, so that is simply an angle bisector. Let's look here at something called the angle bisector theorem. So it says any point of the bisector of an angle is equidistant, there's that word, it's equidistant from the sides of the angle. All right, if I apply that to my little drawing here, it's saying that if I pick any point on this angle bisector, let's pick a point right here, and then I draw a line to each side of the angle itself. And whenever it says you draw a line to the side, it means, and it doesn't say it, but it means a perpendicular line. Not just any line, if you draw a perpendicular line to the sides of the angle. Then it's saying that those are equidistant, which kind of makes sense because this angle goes right through, or the angle bisector goes right through the middle of the angle. So it's just saying no matter where you draw that point, I could pick another one right here, drop perpendicular lines to the sides of the angle, then those would also be congruent. That's all that theorem is saying. We can also construct angle bisectors within an actual triangle. Specifically, we could make 3 of them, right? Because they would bisect each vertex. Okay, so if we do that and we draw all 3 of the angle bisectors, just like with perpendicular bisectors, they will always meet in one point. And we call this point where the angle bisectors meet the incenter of the triangle. Incenter. So with perpendicular bisectors, we talked about the circumcenter and how we could circumscribe a circle around the triangle, and then that thing, the circumcenter, was the center of that. Well, for angle bisectors, it's kind of similar, but for the incenter, we actually inscribe a circle, meaning you draw a circle, the biggest one you can, inside of the triangle so that it touches the walls of the triangle, but it doesn't go outside of it. So that incenter is the very center of an inscribed circle of the triangle. So let's think back to our angle bisector theorem and kind of apply it to the angle bisectors of a triangle. So if we take a look at, let's just look at this angle bisector right here. So remember that theorem said if I pick any point on that angle bisector, I could pick one like right here, for instance. Oops. Right here, and I could draw perpendicular lines to the sides of that angle. It's saying those two things would be congruent. Well, let's specifically pick the one on the bisector right here. Let's pick that incenter. So if I draw straight lines to the sides of the angle, it's saying those are congruent. All right, well, let's look at another angle bisector. What if I did the same thing to this angle bisector over here? Let me pick a different color. All right, so if I look at this angle bisector again, I could pick any point on it. I could pick one right here. But we are interested in picking the incenter to see what happens. All right, and if I drop perpendicular lines here and here, if you notice, it shares one with the other side. It says that those two are congruent to each other. All right, and then let's look at our other angle bisector here. Let me pick a different color. All right, here's my angle bisector. If I pick any point on it at all, but we are going to pick the incenter, and I drop perpendicular lines to either side, and those are also congruent. So what we notice is the incenter. If we draw perpendicular lines to all 3 sides of the triangle, gotta be perpendicular, that those are all congruent. And it makes sense because if we have that inscribed circle right here, we are just drawing a radius of the circle, so they would have to be congruent. Now remember with perpendicular bisectors and their circumcenter, we talked about how in different triangles it could either be inside the circle, it could be it could be inside the triangle, it could be on the triangle if it's a right triangle, or if you have an obtuse triangle, the circumcenter actually met somewhere outside of the triangle. Well, with angle bisectors, just a side note here, the incenter is always going to be inside the triangle. It's never going to be outside the triangle or on the triangle. It'll always be somewhere inside the triangle, no matter what kind of triangle you're dealing with. So angle bisectors actually have another theorem, I guess because they're just so special. So we have another theorem with angle bisectors, something called the triangle angle bisector proportionality theorem. And what this says basically is if you have an angle bisector in a triangle, it divides all the side lengths up in a proportional way. All right, meaning if I've got my angle bisector here, I could say this side is to this one as that side is to that one and set up a proportion just like they kind of showed you and color coordinated it right here. And you can set your proportion up multiple different ways. You could even say it like this. You could say this side is to this one as that side is to that one and solve your proportion that way. Let me show you a specific example here. All right, so we've got a triangle here. We've got an angle bisector right here. As we can see, they show you these little arc marks, meaning BD is an angle bisector. All right, so we know that if it's an angle bisector, it divides everything up, all the side lengths up in a proportional way. So this is a very useful theorem because it can help us find missing side lengths. Like right here, it says side length X. We can find that now. All right, and there's several ways we could set this up. We could say, all right, let's deal with this triangle over here. We could say 5 is to 3.5. This side is to this side, if I write that down. 5 is to 3.5. As, and then if we proportionally do that over here in the correct order, it would be as 12 is to x. This side is to this one. And then from there, we're just cross multiplying. 5 times x, 5x. You can use a calculator if you'd like. That's 3.5 times 12, which gives us 42. Divide both sides by 5. X equals, I believe, that is 8.4. And we could have set it up a whole different way as well. We could have said, for instance, instead of comparing these two sides first, we could have crossed the triangles and said, this side is to this one, 5 is to 12, as this side is to this one, 3.5 is to x. However you would choose to set it up, doesn't matter because you're going to get the same thing. We're still doing 5 times x, we're still doing 3.5 times 12. And there you go. That's angle bisectors in a nutshell.